There is a rhythm to the universe that exists far beyond the ticking of any clock. It moves in scales so vast that entire human civilizations rise and fall between single heartbeats of cosmic change. Tonight, we're going to explore these rhythms together, these grand and patient processes that unfold across timescales almost impossible to comprehend. This is not a journey of urgency or excitement, but rather one of profound stillness, where we can rest in the knowledge that the cosmos moves at its own unhurried pace. The universe is 13.8 billion years old. That number itself is difficult to hold in your mind, difficult to feel in any meaningful way. 13,800,000,000 years. And yet, even within this immense span of time, there are processes still unfolding that will take far longer to complete. There are stars that will outlive our universe's current age many times over. There are black holes that will persist for timescales that make billions of years seem like the briefest flicker. In the quiet of this moment, as you listen to these words, photons of light are traveling through the void between galaxies, journeys they began billions of years before Earth existed. Continents are drifting across our planet's surface, moving at speeds measured in centimeters per year, the same rate at which your fingernails grow. Our entire solar system is making a slow, lazy orbit around the center of the Milky Way galaxy, a journey that takes 225 million years to complete just once. These facts are not meant to make you feel small or insignificant. Instead, they offer a kind of permission to slow down, to recognize that in a universe where change happens over such vast expanses of time, there is no rush, there is no deadline. The universe itself is teaching us patience with every passing moment. Over the next hours, we're going to explore these timescales together. We'll journey from the smallest quantum flickers that happen in attoseconds, trillionths of a second, all the way to the eventual evaporation of black holes over timescales so long they require numbers with more than 100 zeros. We'll move gently through this landscape of time, pausing to appreciate each scale, each rhythm, each patient cosmic process. You don't need to remember every number or every fact. You don't need to work to understand. Simply let these ideas wash over you like waves on a shore, each one arriving in its own time, each one receding back into the depths of deep time. Allow yourself to drift alongside these cosmic processes, to feel the profound stillness that comes from recognizing how slowly, how patiently the universe unfolds. There will be no sudden shifts in tone, no jarring revelations. We will move as the universe moves, steadily and without haste. From the formation of galaxies to the slow drift of continents, from the patient burning of the smallest stars to the eventual fate of all matter itself, we will explore it all with the same gentle curiosity, the same unhurried pace. So settle in, find a comfortable position, let your breathing slow and deepen. The universe has been here for 13.8 billion years. It will be here for trillions more. In this moment, you are suspended in the vast middle of that journey, held safely by forces and timescales that dwarf any individual worry or concern. There is nowhere you need to be, nothing you need to do. The universe will continue its patient unfolding whether you are awake or asleep, whether you are paying attention or drifting away. Let us begin this journey through the slowest processes in existence, through timescales that remind us that patience is not just a virtue, but the fundamental nature of reality itself. Imagine, if you will, that we could take the entire history of the universe and compress it down into a single year. This is not a new idea. The astronomer Carl Sagan popularized this concept in his work, creating what he called the cosmic calendar, a way of visualizing time that allows us to grasp, even slightly, the vast depths of cosmic history. In this calendar, the Big Bang happens at the very first moment of January 1st, at midnight. The universe explodes into existence, space and time beginning their expansion, energy flooding into the void. And then, if we scale everything proportionally, the present moment maps onto December 31st, just before midnight. 12 months, 365 days, an entire year to represent 13.8 billion years of cosmic history. When you use this scale, each month represents approximately 1,150 million years. Each day contains roughly 37.8 million years. Every hour holds 1.58 million years, and each second, each single tick of the cosmic clock, contains 438 years of actual time. Let that settle for a moment. In 1 second of cosmic time, 438 years pass. The entire span of time from the Renaissance to the present day would be less than a single second on this calendar. The entirety of recorded human history, all the empires that have risen and fallen, all the pyramids and cities and civilizations would fit into approximately 11 seconds at the very end of December 31st. On this calendar, our solar system does not form until early September. For more than 8 cosmic months, the universe existed without the sun, without Earth, without any of the familiar landmarks of our local cosmic neighborhood. Galaxies formed and evolved, stars were born and died, entire generations of stellar populations came and went. And still, our solar system had not yet condensed from its primordial cloud of gas and dust. The first simple cells of life appeared on Earth around mid-September in cosmic time. These were not the complex multicellular organisms we associate with life today, but simple bacterial cells, microscopic and patient, slowly learning to harness the energy of the sun through photosynthesis. For billions of years, this would be the only form of life on Earth. Simple, single-celled organisms, reproducing and evolving at a pace that seems glacial even when measured against geological time. Multicellular life, the ancestors of all the plants and animals we know today, did not appear until late November. Think about that. For 10 cosmic months, from January through October, Earth existed without any complex life at all. Just bacteria and archaea, simple cells drifting in primordial oceans, slowly transforming the chemistry of the planet's atmosphere and surface. The first plants emerged on land on December 20th. The dinosaurs, those giants that dominated the planet for so long, appeared on December 25th and went extinct on December 30th. Their entire reign, spanning roughly 165 million years, fits into less than a week on the cosmic calendar. And humans? Modern humans, Homo sapiens, appeared on December 31st at 11:52 p.m. 8 minutes before midnight. Everything that we think of as human history, everything that happened since humans began to farm and build cities and write down their thoughts, all of that happened in the final second before midnight on December 31st. This perspective can be dizzying, even unsettling, but it can also be deeply calming. It reminds us that change happens slowly, that the universe is not in a hurry, that the processes which govern reality unfold across timescales that make our daily concerns, our annual goals, our lifetime achievements, feel like the briefest ripple on an ocean of time. The formation of the first galaxies occurred on January 22nd, roughly a billion years after the Big Bang. These early galaxies were smaller and more irregular than the grand spirals and ellipticals we observe today. They collided and merged, pulled together by gravity, slowly building up into larger and larger structures over billions of years. The Milky Way galaxy, our home, likely took shape through a series of these mergers, smaller galaxies gradually combining into the familiar spiral structure we would recognize today. This process was not quick. It unfolded over billions of years, each collision taking hundreds of millions of years to complete, the gas and stars slowly settling into new orbits, new configurations. Even now, in the present moment, this process continues. The Milky Way is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. But this collision will not happen for another 4.5 billion years. On the cosmic calendar, if we were to extend it into the future, this collision would not occur until sometime in late April of the next cosmic year. When galaxies collide, they do so with a slowness that seems paradoxical, given the violence of the event. Individual stars almost never actually hit each other. The space between stars is so vast that even when two galaxies interpenetrate, passing through each other's spiral arms, the stars themselves sail past each other like ships in a vast ocean. It is only the gravitational interactions, playing out over millions and tens of millions of years, that gradually reshape the galaxies, pulling them into new forms. Think about watching a galaxy collision in real time. You would need to be immortal, patient beyond any human capacity for patience. You would watch for 10,000 years and see almost no change. 100,000 years, and the galaxies would have moved slightly closer together, their spiral arms beginning to distort under mutual gravitational influence. 1,000,000 years, and the changes would be more obvious, but still glacially slow. The entire process, from first approach to final merger, would take hundreds of millions of years to complete. This is the rhythm of cosmic time. This is how the universe moves. Not in sudden jumps or rapid transformations, but in patient, inexorable processes that unfold across timescales that dwarf any individual human life, any civilization, any species. As we compress the entire history of the universe into this single year, we begin to see patterns. We see that most of the year passes without us. We see that the Sun and Earth are relatively recent additions to the cosmic story. We see that life itself took billions of years to move from simple cells to complex organisms, and that the leap from complex organisms to beings capable of contemplating the universe took billions more. There is something profoundly restful in this knowledge. The universe is not hurrying toward any particular destination. It is simply unfolding, moment by moment, across timescales so vast that our longest geological epochs, our ice ages and mass extinctions and continental rearrangements, all appear as brief fluctuations in a much longer, slower rhythm. The cosmic calendar helps us to zoom out, to see ourselves not as the center or culmination of cosmic history, but as a recent development, a late arrival to a party that has been going on for billions of years and will continue for trillions more. And in that perspective, there is a kind of peace. We are not rushed. We are not late. We are simply here, now, in this moment, on December 31st at 11:59 p.m., suspended in the vast sweep of cosmic time. Among all the objects in the universe, stars are perhaps the most patient. They are vast nuclear furnaces, converting hydrogen into helium through fusion reactions at their cores, and this process can sustain them for timescales that challenge our comprehension. But not all stars burn at the same rate. The massive, brilliant blue giants exhaust their fuel in just a few million years, cosmic eye blinks. Our own sun, a medium-sized yellow dwarf, will shine for about 10 billion years total. But there is another class of stars, quiet and dim and often overlooked, that will outlast everything else we can see in the night sky. These are the red dwarf stars. Red dwarfs are the smallest and coolest stars capable of sustaining hydrogen fusion in their cores. They have masses ranging from about 7.5% to about 60% of our Sun's mass. They are dim, often less than 100,000th as bright as the Sun, which means they are essentially invisible to the naked eye despite being the most common type of star in the galaxy. Current estimates suggest that 70 to 80% of all stars in the Milky Way are red dwarfs. But what makes red dwarfs truly extraordinary is their longevity. These stars burn their hydrogen fuel so slowly, so efficiently, that they can continue fusing hydrogen for trillions of years. The smallest red dwarfs could potentially shine for 10 trillion years or more. To put that in perspective, the universe is currently 13.8 billion years old. These tiny stars will still be burning bright long after our Sun has died, long after most of the stars we can currently see have exhausted their fuel and gone dark. 10 trillion years. The number almost loses meaning. It is so far beyond the current age of the universe that it's difficult to find any comparison that makes it feel real. Our Sun has existed for 4.6 billion years and will continue for about 5 billion more before it begins to die. In the time it takes a single red dwarf to exhaust its fuel, 1,000 stars like our Sun could live their entire lives from birth to death. The reason for this extraordinary lifespan lies in the internal structure of red dwarfs. Unlike larger stars, which have distinct layers where fusion happens in the core and the outer envelope remains separate, red dwarfs are fully convective. This means that the material inside the star is constantly mixed with hot plasma rising from the core to the surface and cooler material sinking back down. This convection brings fresh hydrogen fuel from the outer layers down into the core where fusion can occur. In a star like the Sun, only about 10% of the total hydrogen is available for fusion, because only the hydrogen in the core gets hot and dense enough for fusion reactions to take place. The rest of the hydrogen in the outer layers never participates in fusion. But in a red dwarf, because of this complete mixing, nearly 100% of the star's hydrogen can eventually be fused into helium. The star is perfectly efficient, wasting nothing, burning every last atom of fuel over the course of trillions of years. This efficiency comes at the cost of luminosity. Red dwarfs are dim because they burn their fuel so slowly. The fusion reactions in their cores proceed at a leisurely pace, releasing energy gradually rather than in the fierce torrents that power larger stars. This slow burn is what grants them their impossible lifespans. Astronomers have calculated specific lifespans for red dwarfs of different masses. A red dwarf with about half the mass of the Sun will burn for roughly 200 billion years. A red dwarf with a quarter of the Sun's mass will last for about 1 trillion years. The very smallest red dwarfs, right at the lower mass limit where fusion can still occur, could potentially shine for 10 trillion years or even longer. To help grasp these timescales, imagine that the entire current age of the universe, 13.8 billion years, is represented by a single year. On that scale, a red dwarf with a lifespan of 1 trillion years would burn for over 72 years. The smallest, longest-lived red dwarfs would burn for more than 700 years on this compressed timescale. These stars are so slow to evolve that none of them have ever died. Not one. The universe is not old enough. Every red dwarf that has ever formed is still shining, still burning, still fusing hydrogen in its core. There are red dwarfs that formed in the early universe more than 13 billion years ago that are still in the prime of their lives, not even 1% of the way through their total lifespan. This means we have never actually observed what happens when a red dwarf exhausts its fuel. We can model it, we can run computer simulations, we can apply the laws of physics to predict what should happen, but we cannot point to an actual, observed example of a dead red dwarf. They simply have not had time to die yet. Current theories suggest that when a red dwarf finally does exhaust its hydrogen, it will not go through the dramatic transformations that larger stars experience. It will not swell into a red giant, will not shed its outer layers in a planetary nebula, will not explode as a supernova. Instead, it will simply get hotter and smaller, transforming into a hypothetical type of star called a blue dwarf, and then eventually cooling down into a white dwarf, a dense, slowly cooling ember of degenerate matter. But again, this is theoretical. We have never seen it happen. We will not see it happen for trillions of years. Any civilization that witnesses the death of a red dwarf will be living in a universe vastly different from the one we inhabit now. The Milky Way will have long since collided with Andromeda. Most of the gas in galaxies will have been used up to form stars or ejected into intergalactic space. Star formation will have slowed to a trickle and then stopped altogether. The universe will be entering what some cosmologists call the degenerate era, when the only light comes from the slow cooling of stellar remnants and the patient burning of the last red dwarfs. There is something deeply calming about these stars. They are not dramatic or spectacular. They do not explode or flare up into supernovas. They are not visible to our unaided eyes, but they are patient, they are steady, they burn with a constancy that spans timescales longer than almost anything else in the universe. They are reminders that not everything needs to be bright or fast or dramatic to be significant. Sometimes, the most enduring things are the quietest ones, the ones that simply persist, slowly and steadily, across unimaginable spans of time. In the far future, long after our sun has died, long after Earth has been consumed or rendered uninhabitable, the red dwarfs will still be shining. They will be among the last lights in the universe, tiny pinpricks of warmth in an increasingly cold and dark cosmos. And even then, they will not rush. They will continue at their slow, patient pace, burning their fuel atom by atom, year after year, millennium after millennium, eon after eon, for trillions of years into a future we cannot begin to imagine. Our solar system, our sun and all its planets, is not stationary. It moves through space, orbiting the center of the Milky Way galaxy at a speed of approximately 220 kilometers per second. That sounds fast. In human terms, it is fast, about 800,000 kilometers per hour. But the galaxy is so immense that even at this speed, it takes an extraordinarily long time to complete a single orbit. One complete orbit of the Sun around the galactic center is called a galactic year, or sometimes a cosmic year. This journey takes between 225 and 250 million Earth years to complete. The exact duration depends on how you measure the distance to the galactic center and the precise orbital velocity, both of which are difficult measurements with some uncertainty. But the general scale is clear. Roughly 230 million years for one complete orbit. To put this in perspective, the Sun is approximately 4.6 billion years old. In that time, it has completed about 20 orbits around the galaxy. Only 20. In the Sun's entire lifetime so far, from its birth in a collapsing cloud of gas and dust to the present moment, It has made roughly 20 lazy circles around the galactic center. When the Sun completed its last orbit, the one just before the current one, the continents were in different positions. Pangaea, the supercontinent that contained all of Earth's landmasses, had not yet formed. The Appalachian Mountains were young and tall, recently thrust up by the collision of continental plates. Trilobites still crawled across the seafloor. The first reptiles were just beginning to evolve from amphibian ancestors. There were no dinosaurs, no mammals, no flowering plants. The world was alien, unrecognizable. Go back one orbit before that, and the world is even stranger. The first vertebrates were just beginning to crawl out of the oceans onto land, developing lungs and limbs adapted for terrestrial life. The ancestors of all land animals were taking their first uncertain steps onto a landscape of ferns and primitive plants. And the Sun has made only about 20 of these orbits in its entire existence. The galaxy itself rotates in a complex way. It is not like a solid disk spinning uniformly. Different parts of the galaxy rotate at different speeds. Stars closer to the galactic center orbit faster, completing a circuit in a shorter time. Stars farther out, in the outer reaches of the galactic disk, orbit more slowly. This is called differential rotation. But there is an interesting observation that adds another layer to this slow cosmic dance. Research published in the monthly notices of the Royal Astronomical Society found that all disk galaxies, regardless of their size or mass, appear to rotate at approximately the same rate at their outer edges. Specifically, the outer disks of galaxies, both small dwarf galaxies and massive spirals, complete one rotation approximately every billion years. This is a remarkable finding. It suggests a kind of universal rhythm to galactic rotation, a timescale that seems to be fundamental to the structure of disk galaxies. 1 billion years for the outer reaches of a galaxy to complete a single rotation. 1 billion years, 1/7 of the age of the universe, for the great wheel to turn once at its edge. Our Sun is not at the outer edge of the Milky Way. It is located about 8 kiloparsecs, roughly 26,000 light-years, from the galactic center. This places us in the middle regions of the galactic disk, in a spiral arm called the Orion arm, or the local arm. And at this distance, the orbital period is shorter than at the outer edge, but still measured in hundreds of millions of years. As the Sun orbits, it does not move in a perfect circle. Its orbit is slightly elliptical, and the Sun also bobs up and down relative to the galactic plane. This vertical motion has a period of about 64 million years, meaning the Sun crosses the midplane of the galaxy roughly every 32 million years. Some researchers have speculated that these crossings might correlate with mass extinction events on Earth, as the changing gravitational environment disturbs comets in the outer solar system, potentially sending them into the inner solar system where they could impact Earth. But this hypothesis remains controversial and not definitively proven. What is clear is that the Sun's motion through the galaxy is slow and steady. Over the course of its galactic orbit, it encounters different environments. Sometimes it is in a spiral arm where star formation is active and the interstellar medium is denser. Sometimes it is between spiral arms, in quieter regions where stars are more spread out. But these changes unfold over tens of millions of years. From a human perspective, from the perspective of recorded history, or even the entire span of human evolution, the galactic environment appears essentially static. The galaxy itself is not static, of course. It is constantly evolving. Stars are forming in molecular clouds, living there, lives and dying. some exploding as supernovas and enriching the interstellar medium with heavy elements. The spiral arms are not permanent structures, but rather density waves, regions where stars and gas temporarily bunch up as they orbit, creating the appearance of spiral structure, even though individual stars are constantly moving in and out of the arms. And the galaxy is on a collision course with Andromeda, as we have mentioned. In about 4.5 billion years, the two galaxies will begin to merge. But even this collision is a slow process. The initial approach will take hundreds of millions of years. The galaxies will pass through each other, their stars sailing past like ships in the night, but their gravitational interactions will distort both galaxies, pulling out long tidal tails of stars and gas. They will separate, slow down, and then fall back together again, passing through each other a second time. This process will repeat several times over the course of billions of years, until finally the two galaxies merge completely into a single, larger elliptical galaxy. Even this, one of the most dramatic events in the future of our local cosmic neighborhood, unfolds over timescales of billions of years. There is no moment of sudden collision, no catastrophic impact. Just a slow gravitational dance playing out over eons. The rotation of our galaxy, the orbit of our sun, these are not processes we can directly perceive. We cannot feel the motion, cannot see the change from day to day or year to year. These rhythms are too slow, too vast. They exist on timescales that require us to think in millions and hundreds of millions of years. And yet, they are as real and as constant as the rotation of Earth on its axis or the orbit of Earth around the Sun. In a sense, we are all traveling through space together, riding on this great slow wheel as it turns around the galactic center. Every star we see in the night sky is making this same journey, each at its own pace, each following its own orbital path. And the journey will continue long after we are gone. Long after Earth has cooled and gone dark, the Sun will still be orbiting the galaxy, making its patient circuit, a journey that will continue until the Sun itself finally exhausts its fuel and dies billions of years from now. Beneath our feet, the ground itself is moving. Not quickly, not in any way we can perceive in our daily lives, but the continents, those vast rafts of rock that we think of as permanent and stable, are drifting across the surface of the planet at speeds measured in centimeters per year. This movement is called plate tectonics, and it is one of the most important discoveries in the history of Earth science. The Earth's outer shell, the lithosphere, is broken into about 8 major plates and several smaller ones. These plates float on the partially molten asthenosphere beneath them, driven by convection currents in the Earth's mantle. The heat from the Earth's core causes rock to rise, spread laterally beneath the lithosphere, and then sink again, creating a slow churning motion that drags the plates along. The speed of this motion varies depending on the plate and the location. In some places, like the North Atlantic, the rate of movement is only about 1 centimeter per year. In other places, like the Pacific, plates can move at speeds of 4 centimeters per year or more. Some estimates for the fastest moving plates reach up to 10 centimeters per year. To give a sense of scale, your fingernails grow at about 3 to 4 centimeters per year. The continents are drifting at roughly the same speed that your fingernails grow. This seems impossibly slow. How could movement this gradual possibly reshape the planet? And yet, over millions and tens of millions and hundreds of millions of years, this slow drift has dramatic consequences. Continents collide and form mountain ranges. Oceans open and close. Supercontinents assemble and, then break apart again in a cycle that has repeated several times over Earth's history. The most recent supercontinent was Pangaea, a name meaning all Earth. Pangaea formed approximately 335 million years ago, as the earlier continents slowly collided and merged. It existed as a single landmass for roughly 160 million years, from the late Paleozoic into the Mesozoic era. Then, about 175 million years ago, Pangaea began to break apart. The breakup was not instantaneous. It did not happen all at once. Instead, rifts slowly formed as tectonic forces pulled the supercontinent in different directions. These rifts gradually widened over millions of years, filling with water to form new oceans. The Atlantic Ocean, which separates the Americas from Europe and Africa, is a direct result of Pangaea's breakup. The ocean is still widening today, growing by a few centimeters each year as the mid-Atlantic ridge continues to produce new oceanic crust. But Pangaea was not the first supercontinent. Before Pangaea, there was Gondwana, and then Pannotia, and before that, Rodinia, and before that other supercontinents whose names and configurations are still being worked out by geologists. The pattern suggests a cycle, called the supercontinent cycle, in which continents drift together to form a supercontinent, remain assembled for 100 million years or so, and then break apart again. The cycle repeats approximately every 600 million years. This cycle is closely related to, but distinct from, the Wilson cycle, named after the geologist John Tuzo Wilson. The Wilson cycle describes the opening and closing of individual ocean basins. An ocean forms when a continent rifts apart. The ocean grows as new oceanic crust is created at a mid-ocean ridge. Eventually, the ocean reaches its maximum size and then begins to shrink as subduction zones form, consuming oceanic crust. Finally, the ocean closes completely as the continents on either side collide, forming a mountain range. The cycle then begins again as new rifts form and new oceans open. The Atlantic Ocean is currently in the growing phase of its Wilson cycle. It has been widening for about 170 million years since Pangaea began to break up. But eventually, perhaps hundreds of millions of years from now, the Atlantic will begin to close. Subduction zones will form, and the ocean floor will begin to be consumed back into the mantle. The Americas will drift back toward Europe and Africa, and eventually, in perhaps 250 million years or so, a new supercontinent will form. Scientists have proposed several names and configurations for this future supercontinent, depending on how the continents are predicted to collide. Names like Pangaea Proxima, Novo-Pangaea, Amasia, and Orica have been suggested. But the details are uncertain. The exact path that the continents will take, the precise arrangement of the next supercontinent, these things depend on the complex dynamics of mantle convection and plate movements, which are difficult to predict over such long timescales. What is certain is that the process will be slow. The continents will drift at centimeters per year. Mountain ranges will rise as continents collide, but the rise will be gradual, measured in millimeters per year. Over millions of years, these millimeters add up. The Himalayas, the tallest mountain range on Earth, are still rising today as the Indian plate continues to push into the Eurasian plate. They rise at about 5 millimeters per year. It has taken tens of millions of years for them to reach their current heights, and they will continue to rise for millions of years more. There is something almost meditative about imagining these processes. The slow drift of continents, the gradual opening and closing of oceans, the patient rise of mountains. These are changes that happen on timescales far beyond human experience, and yet they are constantly occurring, every day, every moment. The ground beneath your feet is moving imperceptibly as part of a grand, slow dance that has been ongoing for billions of years and will continue for billions more. When we think about geological time, we often focus on the dramatic events: volcanic eruptions, earthquakes, meteor impacts. These are the moments of sudden change, the catastrophes that reshape the planet in hours or days. But the underlying processes, the processes that create the conditions for these dramatic events, are slow and patient. The buildup of stress along a fault line takes decades or centuries. The creation of the magma chamber beneath a volcano takes millennia. The movement of continents that creates the tectonic stresses in the first place takes millions of years. The Earth is patient. It moves at its own pace, unhurried by human concerns or human timescales. And in that patience, there is a lesson. Change does not have to be fast to be profound. Movement does not have to be visible to be real. The most significant transformations can be the slowest ones, the ones that unfold over timescales so vast that they are invisible to individual observers, but nonetheless reshape the entire face of the world. Light moves fast. In fact, it moves at the fastest speed possible in our universe. The speed of light in a vacuum is exactly 299,792,458 meters per second. This value is so fundamental to physics that it is now used to define the meter itself. A meter is the distance light travels in 1/299,792,458th of a second. At this speed, light can circle the Earth's equator about 7.5 times in a single second. It can travel from the Earth to the Moon, a distance of roughly 384,000 kilometers, in about 1.3 seconds. From the Sun to the Earth, a distance called 1 astronomical unit, or roughly 150 million kilometers, light takes about 8 minutes and 20 seconds. These are impressive speeds and short travel times when we're talking about distances in our solar system. But when we expand our view to the scale of the galaxy or the universe as a whole, even light becomes slow. Even traveling at the ultimate cosmic speed limit, light takes years, centuries, millennia, millions of years to cross the vast gulfs between stars and galaxies. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system, located about 4.2 light-years away. This means that light from Proxima Centauri takes 4.2 years to reach us. When we look at Proxima Centauri through a telescope, we are not seeing the star as it is now, in this moment. We are seeing it as it was 4.2 years ago. We are looking back in time. This effect becomes more pronounced the farther we look. The center of our Milky Way galaxy is approximately 26,000 light-years away. Light from the galactic center takes 26,000 years to reach us. When we observe the supermassive black hole at the galaxy's center, we are seeing it as it was 26,000 years ago, long before recorded human history began. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. The light we see from Andromeda left that galaxy 2.5 million years ago, when our ancestors were just beginning to diverge from other primates, when the genus Homo was just emerging. And the most distant objects we can observe are much, much farther away. The current record for the most distant galaxy ever observed is held by a galaxy designated JD's GSZ 14-0, which recent observations suggest existed when the universe was only about 290 million years old. Light from This galaxy has been traveling through space for more than 13.5 billion years to reach us. When we observe this galaxy, we are seeing it as it was in the very early universe, when the first generations of stars and galaxies were just beginning to form. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light-years. This is larger than 13.8 billion light-years, which you might expect given the age of the universe, because space itself has been expanding during the time that light has been traveling toward us. Objects that were closer when they emitted their light have since moved farther away due to the expansion of space. But even this immense observable universe represents only a fraction of the total universe. There are regions of space so far away that light from them has not had time to reach us yet, and due to the acceleration of cosmic expansion, light from these regions may never reach us. We are surrounded by a horizon, not because there is nothing beyond it, but because the light from beyond has not yet had time to arrive. Think about that for a moment. There are stars that exist, that are shining right now, whose light will not reach Earth for millions or billions of years. There are galaxies so distant that even though they have existed for billions of years, we cannot see them yet because their light is still in transit, still making the long journey across the expanding void between galaxies. And conversely, there is light that left Earth billions of years ago that is now reaching distant parts of the universe. If there are observers in a galaxy 10 billion light-years away looking at our Milky Way right now, they are not seeing the galaxy as it exists today. They are seeing it as it was 10 billion years ago, when the Sun and Earth did not yet exist, when the galaxy was younger and smaller, still assembling itself from the collision and merger of smaller proto-galaxies. This is the nature of light's journey through the cosmos. At cosmic scales, even moving at the fastest possible speed, it takes time, enormous amounts of time, to cross the distances between objects. And so we live in a universe where the present moment is fragmented, where different parts of the universe are visible to us at different stages of their history, all coexisting in our telescopes, a collage of past light arriving in our present. There is something deeply strange and also deeply calming about this. It means that when we look up at the night sky, we are not seeing the universe as it is now. We are seeing a collection of moments from the past, some recent, some ancient, all mixed together. The light from the moon is about 1 second old when it reaches our eyes. The light from the sun is 8 minutes old. The light from the nearest stars is years old. The light from distant galaxies is millions or billions of years old. We are surrounded by the past. We swim in it. And yet, from our perspective, it all appears to be happening now, in this moment, because it is all arriving now. The universe presents itself to us not as it is, but as it was, with different regions visible at different moments in their history. This also means that there is no universal now in the cosmos. Due to the finite speed of light and the expansion of space, different observers in different locations will have different definitions of what is happening right now in distant parts of the universe. The present moment is local, not universal. Time itself becomes relative at cosmic scales, and light will continue its patient journey. Photons emitted billions of years ago are still traveling through space, some of them destined to arrive at Earth in our telescopes, some of them destined to travel forever through the expanding void, never encountering anything, never being absorbed, just traveling endlessly through the darkness. In the far future, as the universe continues to expand and accelerate, more and more of the universe will slip beyond our observable horizon. Light from distant galaxies will be redshifted so far that it becomes effectively undetectable. Eventually, in trillions of years, The only galaxies visible from the Milky Way will be the ones gravitationally bound to us in our local group. All the other galaxies will have receded beyond the horizon, their light unable to ever reach us no matter how long we wait. But even then, the light from those galaxies will still be traveling. It will be out there in the void between galactic superclusters, photons journeying through space, remnants of galaxies that existed billions of years ago, carrying information about a universe that once was, even if there is no one left to receive that information. We have been exploring the slowest processes in the universe, the grand patient rhythms that unfold over millions and billions of years. But to truly appreciate the vast range of timescales in nature, we should also consider the opposite end of the spectrum, the fastest processes, the briefest moments that physics allows. At the quantum scale, events happen in timescales almost impossibly short. An attosecond is 1/quintillionth of a second, 1/billionth of a billionth of a second. To put this in perspective, an attosecond is to a second what a second is to the age of the universe. If you could slow time down so that 1 second felt like the entire 13.8 billion year history of the cosmos, an attosecond would feel like a single second within that vastly expanded time frame. Attosecond physics is the study of processes that happen on these timescales. In 2023, the Nobel Prize in Physics was awarded to Pierre Agostini, Ferenc Krauss, and Anne Lhuillier for their work developing experimental methods to generate and study attosecond pulses of light. This achievement opened up the ability to observe and measure phenomena that were previously too fast to capture. What happens on attosecond timescales? One of the most important processes is the movement of electrons in atoms. When an electron absorbs a photon and jumps from one energy level to another, or when it emits a photon and falls to a lower energy level, these transitions happen extremely quickly. The timescale for these processes is often measured in femtoseconds, which are thousandths of a billionth of a second, or even attoseconds. For example, when light hits a material and ejects an electron, a process called the photoelectric effect, the ejection happens within attoseconds to femtoseconds. The electron absorbs the photon's energy and leaves the atom in a time so brief that even calling it a moment seems to give it too much duration. Similarly, when atoms or molecules interact with intense laser light, the electrons can be briefly pulled away from the nucleus and then snapped back, emitting bursts of high-energy photons in the process. These interactions happen on attosecond timescales. The motion of electrons in response to the oscillating electric field of the laser happens so quickly that only attosecond techniques can capture it. But even attoseconds are not the shortest timescales in physics. There is a theoretical limit called the Planck time, which is approximately 5.4 times 10 to the negative 44 seconds. This is the time it takes for light to travel 1 Planck length, which is the smallest distance that has meaning in quantum mechanics. Below the Planck time, our current theories of physics break down. We do not have a quantum theory of gravity, and so we cannot meaningfully describe what happens at timescales shorter than the Planck time. But we do not need to go all the way down to Planck scales to find incredibly brief moments. In particle physics, many interactions and decays happen on timescales of nanoseconds, billionths of a second, or even picoseconds, trillionths of a second. When subatomic particles collide at high energies in particle accelerators, they can create exotic particles that exist for only a fraction of a nanosecond before decaying into other particles. For instance, the top quark, the heaviest known fundamental particle, has a lifetime of approximately 5 times 10 to the negative 25 seconds. That is half a septillionth of a second. The top quark is created in high-energy collisions and almost immediately decays into other particles. It exists for such a brief time that it does not even have enough time to form bound states with other quarks. It decays before it can form a hadron. These incredibly short timescales stand in stark contrast to the vast, slow processes we have been discussing. And yet, both extremes coexist in the same universe. The same physical laws that allow electrons to jump between energy levels in attoseconds also govern the slow burn of red dwarf stars over trillions of years. The same quantum mechanics that describes the decay of the top quark in half a septillionth of a second also underlies the processes that drive the patient drift of continents. There is a kind of symmetry to this, a balance between the incredibly fast and the incredibly slow. And both extremes are far removed from human experience. We live in a middle ground where a second is a meaningful unit of time, where minutes and hours and days structure our lives. But the universe operates on timescales both far shorter and far longer than anything we directly experience. It is worth pausing to appreciate this range. From the Planck time, 5.4 times 10 to the negative 44 seconds, to the timescale of black hole evaporation, which we will explore shortly, measured in 10 to the 100 years or more, the universe encompasses a range of timescales spanning more than 140 orders of magnitude. That is 140 factors of 10 from the shortest moments to the longest epochs. Human perception spans perhaps 7 or 8 orders of magnitude in time, from the fastest events we can perceive, around a few tens of milliseconds, to a human lifetime of a few billion seconds. The universe's timescales extend far beyond this in both directions. And yet, despite this enormous range, there is a consistency to the laws of physics. The same fundamental equations describe both the rapid quantum transitions and the slow stellar evolution. Time itself, as far as we can tell, flows uniformly, second by second, whether those seconds are filled with quadrillions of quantum events or represent the tiniest fraction of a galactic orbit. In quantum mechanics, there is also a fascinating relationship between time and energy through the Heisenberg uncertainty principle. The principle states that the product of the uncertainty in energy and the uncertainty in time is always greater than or equal to a specific value related to Planck's constant. This means that events that happen very quickly can have large uncertainties in their energy. Particles can briefly violate energy conservation on very short timescales, borrowing energy from the vacuum and then returning it so quickly that the violation cannot be detected. This leads to phenomena like virtual particles, which pop in and out of existence on incredibly brief timescales, too short to be directly observed, but whose effects can be measured through subtle influences on other particles and fields. The vacuum itself, rather than being empty, is a seething sea of quantum activity, particles and antiparticles constantly being created and annihilated on timescales far too brief for us to perceive. But all of this furious quantum activity, all these attosecond transitions and femtosecond reactions, they happen within a universe that, at large scales, moves with extraordinary patience. The quantum foam of spacetime churns at the Planck scale, while galaxies drift through space over billions of years. Both are true simultaneously. Both are part of the same reality. There is something almost paradoxical about this, and also something deeply satisfying. The universe contains multitudes. It is both fast and slow, both fleeting and eternal, both quantum uncertainty and cosmic inevitability. And we exist somewhere in the middle, able to contemplate both extremes, able to measure attoseconds And imagine trillions of years, even though our own existence spans only a few dozen revolutions of Earth around the Sun. If red dwarf stars represent extraordinary patience on the scale of trillions of years, there is an even more patient process lurking in the universe. It is a process so slow that it makes the trillion-year lifespan of a red dwarf seem brief by comparison. This is the evaporation of black holes through a quantum process called Hawking radiation. In 1974, the physicist Stephen Hawking made a remarkable prediction. He showed that black holes, which were thought to be completely black, absorbing everything and emitting nothing, actually emit a faint thermal radiation due to quantum effects near the event horizon. This radiation is now called Hawking radiation. The mechanism is subtle and arises from quantum field theory in curved space-time. Near the event horizon of a black hole, pairs of virtual particles are constantly being created out of the vacuum, as we discussed earlier. Normally, these particle pairs annihilate each other almost immediately. But near the event horizon, something different can happen. One particle of the pair can fall into the black hole, while the other escapes. To an outside observer, it appears as though the black hole has emitted a particle, but this emission comes at a cost. The black hole loses mass, very slightly, with each particle that escapes. Over time, if the black hole does not absorb additional matter to replenish its mass, it will slowly evaporate, losing mass, particle by particle through Hawking radiation, until eventually it disappears completely. The rate at which a black hole evaporates depends on its mass. Smaller black holes evaporate faster than larger ones. In fact, the temperature of the Hawking radiation is inversely proportional to the mass of the black hole. A smaller black hole is hotter and radiates more intensely. A larger black hole is cooler and radiates very, very slowly. For a black hole with the mass of our Sun, the evaporation timescale is approximately 10 to the 67 years. That is a 1 followed by 67 zeros. 10,000 trillion years. This is vastly, incomprehensibly longer than the current age of the universe. It is longer than the lifespans of even the smallest red dwarfs by a factor of more than 10 million trillion. For a supermassive black hole, the kind found at the centers of galaxies, with masses of millions or billions of solar masses. The evaporation timescales are even longer. A black hole with 1 billion solar masses would take approximately 10 to the 98 years to evaporate. And the largest supermassive black holes with tens of billions of solar masses could take more than 10 to the 100 years. 10 to the 100 years. This number is sometimes called a googol, and it is so large that it is difficult to find any physical process that operates on a comparable timescale. It is a number larger than the number of atoms in the observable universe, which is estimated at around 10 to the 80. It is a timescale that makes the age of the universe seem like an eye blink. To help grasp these numbers, imagine that the current age of the universe, 13.8 billion years, is compressed down to a single second. On that scale, the evaporation of a solar mass black hole would take about 10 to the 48 years. The evaporation of a supermassive black hole would take far, far longer, timescales that cannot be meaningfully represented even on this compressed scale. And yet, according to our current understanding of physics, this is what will happen. In the far, far future, long after all the stars have burned out, long after galaxies have merged and star formation has ceased, long after the universe has cooled and darkened, the black holes will remain. And they will evaporate, slowly and patiently, over timescales that dwarf everything else we have discussed. In the final stages of a black hole's evaporation, when it has lost most of its mass and become very small, the process accelerates. The temperature of the Hawking radiation increases, the rate of mass loss increases, and in the final moments, the black hole releases its remaining mass energy in a brief burst of radiation. But even this final burst, dramatic as it might seem, comes at the end of a process that has taken an almost unimaginable span of time. It is worth noting that Hawking radiation has never been directly observed. Black holes in the current universe are much colder than the cosmic microwave background radiation that fills space, which has a temperature of about 2.7 Kelvin. The Hawking radiation from a solar mass black hole would have a temperature of only about 60 billionths of a Kelvin, far too cold to detect against the background. Only very small black holes with masses less than the Moon would be hot enough to emit detectable Hawking radiation, and we have no observational evidence that such small black holes exist. So, like the death of a red dwarf, the complete evaporation of a black hole is theoretical. We have strong theoretical reasons to believe it will happen, based on our understanding of quantum mechanics and general relativity. But we have never observed it. We will not observe it. No civilization will observe it unless they exist in a universe so far in the future that it is unrecognizable compared to the cosmos we see today. By the time black holes begin to evaporate in earnest, the universe will be in what cosmologists call the black hole era. This is an epoch in the far future when black holes are the dominant objects in the universe, everything else having decayed or dissipated. Stars will have long since burned out. Planets will have spiraled into their dead stellar remnants or been ejected into interstellar space. Even the protons and neutrons that make up ordinary matter may have decayed into lighter particles, though this is speculative and depends on physics beyond the current standard model. In the black hole era, the universe will be cold and dark, illuminated only by the faint glow of Hawking radiation from evaporating black holes. And this era will last far, far longer than the stelliferous era we currently inhabit, the era of stars. The stelliferous era will last perhaps 100 trillion years until the last red dwarfs burn out. The black hole era will last for 10 to the 100 years or more until the last black holes evaporate. And then what? After the black holes are gone, the universe will enter what some call the dark era, a time when the only things left are the slowly cooling remnants of matter, photons, and neutrinos, and perhaps some exotic particles that we have not yet discovered. The universe will be nearly empty, nearly uniform, approaching a state of maximum entropy where no further change is possible. This is the ultimate fate of the universe according to current cosmological models, assuming the expansion of the universe continues to accelerate as it appears to be doing. The universe will expand forever, cooling and darkening, until eventually it reaches a state called heat death, where all gradients have been smoothed out, all energy has been dissipated, and no further work can be done. Time will still pass, in some sense, but nothing will change. The universe will be still. But before that final stillness, there will be the long, patient evaporation of the black holes, a process so slow that it makes everything else we have discussed seem hurried by comparison. It is the ultimate expression of cosmic patience, the final act in the drama of a universe slowly approaching equilibrium. We have explored many timescales already: the 230 million years of a galactic orbit, the trillions of years that red dwarfs will burn, the 10 to the 67 years it will take for a solar mass black hole to evaporate. But even these immense timescales are just the beginning when we consider the full future of the universe. If we extend our timeline far enough into the future, we encounter epochs and eras that are defined more by absence than by presence. The far future is a story of things ending, processes completing, systems winding down toward equilibrium. The stelliferous era, the current era of stars, will last approximately 100 trillion years from shortly after the Big Bang until the last red dwarfs finally exhaust their fuel. This is roughly 7,000 times the current age of the universe. If you represented the entire stelliferous era as a single year, the current age of the universe would be about 5 hours. All of recorded human history would be a fraction of a second. During the later stages of the stelliferous era, star formation will slow and eventually cease. The reservoirs of gas that form new stars will be exhausted, either consumed by existing stars or ejected from galaxies by supernova explosions and stellar winds. The last generation of stars will be small red dwarfs, which will burn for trillions of years, slowly fading as they consume their hydrogen. When the last red dwarfs finally go dark, around 100 trillion years in the future, the stelliferous era will end. What comes next is the degenerate era, when the primary objects in the universe will be stellar remnants, white dwarfs, neutron stars, and black holes. These objects no longer produce energy through fusion. They shine, if at all, only from the slow release of residual heat. White dwarfs, the cooling remnants of sun-like stars, will take trillions upon trillions of years to cool to the background temperature of the universe. As they cool, they will fade from white to red to brown to finally becoming black dwarfs, dark and cold, emitting no visible light. The timescale for this cooling is uncertain, but estimates suggest 10 to the 15 years or more for a white dwarf to cool completely. But even as the white dwarfs cool, other processes may be at work. If protons are not perfectly stable, if they can decay into lighter particles, then over timescales of 10 to the 36 to 10 to the 45 years, even the solid matter of white dwarfs and dead planets and asteroids will slowly disintegrate, one proton at a time, releasing tiny bursts of energy as each proton decays. Proton decay is predicted by some theories that attempt to unify the fundamental forces of physics, but it has never been observed. Experiments have set lower limits on the proton lifetime at greater than 10 to the 34 years, but the true lifetime, if protons decay at all, could be much longer. If proton decay happens, it will reshape the matter of the universe over timescales far longer than the age of the universe to date. As the degenerate era progresses, gravitational interactions will continue to shape the distribution of matter. Stars and stellar remnants in galaxies will occasionally encounter each other, and these close encounters can result in objects being ejected from the galaxy entirely or falling into the central black hole. Over timescales of 10 to the 19 to 10 to the 20 years, galaxies will gradually evaporate, losing most of their stars to intergalactic space while their central black holes grow larger. The ejected stars and remnants will drift through the expanding space between galaxies, isolated and alone. They will continue to cool, continue to fade until they become indistinguishable from the background. And the central black holes, having consumed or ejected everything nearby, will be left in isolation, slowly beginning their long evaporation. This brings us to the black hole era, which will last from roughly 10 to the 40 years to 10 to the 100 years or beyond, depending on the mass of the black holes. During this era, the dominant process is the slow evaporation of black holes through Hawking radiation. As we discussed, this process is extraordinarily slow for large black holes, but it is relentless. Given enough time, every black hole will evaporate completely. The energy released by Hawking radiation during these evaporations will be the last significant source of energy in the universe. It will be feeble, spread out over immense spans of time, but it will be there, a last flickering of activity before the final silence. And after the black holes, the dark era, an epoch of almost perfect stillness. The universe will be filled with photons, neutrinos, and perhaps occasional electrons and positrons, all separated by vast distances. There will be no stars, no planets, no black holes, just an expanding void growing ever colder and ever more dilute. In this final era, time becomes almost meaningless. There are no processes left to mark its passage. There are no clocks, no cycles, no changes. The universe will have reached a state very close to maximum entropy, and in the absence of any gradients, any differences in energy or temperature, there is nothing to drive change. Some theories suggest that, even in this far future, random quantum fluctuations could occasionally create interesting structures, perhaps even new universes budding off from quantum tunneling events. But these are speculative ideas, far beyond what we can currently test or confirm. What is clear from our current understanding is that the universe is on a one-way journey from a hot, dense, highly ordered state shortly after the Big Bang to a cold, dilute, highly disordered state in the far future. This journey is driven by the second law of thermodynamics, which states that entropy, the measure of disorder, always increases in a closed system. The universe is running down, slowly approaching equilibrium. But this rundown happens slowly. Remarkably, impossibly slowly. The timescales involved are so vast that they make the entire history of the universe to date seem like the briefest prelude to a story that will unfold over timescales measured in googles of years. And yet, from our perspective, embedded in this brief early epoch, these timescales are almost comforting. They remind us that the universe is in no hurry, that change happens slowly, that even the largest, most dramatic processes unfold over timescales that make our individual lives, our civilizations, our entire species seem like fleeting moments. There is a kind of peace in that. The universe will be here, continuing its patient journey toward equilibrium long after we are gone. The processes that govern cosmic evolution do not care about human timescales or human concerns. They simply continue, second by second, year by year, eon by eon, following the laws of physics with perfect consistency and infinite patience. We have journeyed through vast expanses of time, from the attosecond transitions of electrons to the Google year evaporation of black holes, from the 13.8 billion year history of the universe to the 100 trillion year future of the stelliferous era. We have explored the slow drift of continents, the patient burning of red dwarfs, the lazy orbit of our sun around the galaxy. And through all of this, a pattern has emerged. The universe operates on timescales far longer than we can directly experience. Change happens, but it happens slowly. Even the most dramatic events, the ones that reshape galaxies or extinguish stars, unfold over millions and billions of years. From a human perspective, this can be difficult to grasp. Our lives are structured by days and weeks and years. We think in terms of decades, perhaps centuries if we're considering historical trends. The idea of millions or billions of years is intellectually comprehensible but emotionally difficult to hold. And yet, understanding these timescales can change how we see ourselves and our place in the cosmos. It can provide a sense of proportion, a reminder that many of the things we worry about, many of the urgencies that dominate our daily lives, are fleeting when set against the backdrop of cosmic time. This is not to say that our concerns are not real or important, they are. But there is also value in occasionally stepping back and recognizing the vast, patient rhythms of the universe within which our brief lives are embedded. Think about the light from distant stars. That light has been traveling for years or centuries or millennia before it reaches your eyes. When you look up at the night sky, you are seeing not the present, but a collection of pasts all arriving in your moment. Some of those stars may no longer exist. Their light is still traveling toward us, carrying information about a star that has already died. Think about the continents drifting beneath your feet. Right now, at this moment, North America and Europe are moving apart by a few centimeters. The Atlantic Ocean is widening. In a few million years, it will be noticeably wider. In a few 100 million years, it may begin to close again. This process will continue regardless of what happens to humanity, regardless of our civilizations or our technologies or our concerns. Think about the Sun, orbiting the galaxy every 230 million years. When the Sun completes its next orbit, Earth will have circled the Sun 230 million times. The continents will be in different positions. New mountain ranges may have risen. Old mountains may have eroded away. And the stars in the night sky may be slightly different, as nearby stars drift in their own orbits relative to the Sun. These processes connect us to the deep past and the distant future. They remind us that we are part of something much larger and longer-lived than ourselves. The atoms in our bodies were forged in the cores of stars that died before the Sun was born. The carbon in our cells, the iron in our blood, the calcium in our bones, all of these elements were created by nuclear fusion in stellar cores and then scattered into space by supernova explosions. We are, quite literally, made of stardust. And when we die, those atoms will return to the environment to be incorporated into other structures, other organisms, other worlds, perhaps. The matter that makes us up is ancient, having existed since shortly after the Big Bang, and it will continue to exist long after we are gone. In this sense, we are temporary patterns, brief organizations of matter and energy, that exist for a few decades before dissipating. But the matter itself, the fundamental substance of our being, is nearly eternal. It has persisted for 13.8 billion years and will persist for trillions more. There is a kind of continuity in this, a connection to the deep history of the cosmos and its distant future. We are not separate from the universe. We are the universe, temporarily arranged in a form capable of contemplating its own existence, and the universe itself, we should remember, is still young. If the stelliferous era lasts 100 trillion years, and the universe is currently 13.8 billion years old, then the universe has completed less than 1/10,000th of the star-forming phase of its history. We are living in the very early universe, the first fraction of a percent of the time when stars will shine. All of human history, all of the time from the first stirrings of life on Earth to the present day, has occurred in this tiny sliver at the very beginning of cosmic time. We are early. We are among the first civilizations, the first beings capable of looking up at the stars and wondering about their nature, to emerge in a universe that will continue for trillions upon trillions of years. This perspective can be humbling. It can make us feel small, but it can also be empowering. We are part of this grand story. We are among the first chapters in a narrative that will unfold over timescales we can barely imagine. And while we may not see the end of that story, while we may not witness the death of the last red dwarf or the evaporation of the final black hole, we can still appreciate the arc of it, the patient unfolding of processes governed by physical law, And perhaps in appreciating these timescales, we can also find a sense of calm, a recognition that the universe is not rushed, that there is time. That change, even dramatic change, happens slowly and patiently, following patterns that have been consistent for billions of years and will remain consistent for billions more. The slow cosmic time we have explored tonight is not just a collection of interesting facts. It is an invitation to shift our perspective, to see ourselves as part of a much larger temporal landscape, to recognize that while our individual moments are brief, they are connected to processes and patterns that span the entire history and future of the cosmos. Consider, too, the orbital mechanics that govern our solar system. Earth completes one orbit around the Sun every 365.25 days. This is the rhythm that structures our years, our seasons, the cycle of planting and harvest that has sustained human civilization since its inception. But Earth's orbit is not perfectly stable over very long timescales. The gravitational influence of other planets, particularly Jupiter and Saturn, causes subtle variations in Earth's orbital parameters over periods of tens of thousands and hundreds of thousands of years. These variations are called Milankovitch cycles, named after the Serbian scientist Milutin Milankovic, who calculated them in the early 20th century. They include changes in the eccentricity of Earth's orbit, the tilt of Earth's axis, and the precession of the equinoxes. These cycles occur on timescales of 23,000, 41,000, and 100,000 years, and they are believed to be significant drivers of Earth's ice age cycles. The fact that variations in Earth's orbit on timescales of tens of thousands of years can trigger ice ages lasting tens of thousands of years is itself a testament to the patience of geological and climatological processes. An ice age does not appear overnight. It builds slowly as summers become slightly cooler and winter snow fails to fully melt, accumulating year after year, century after century, gradually building massive ice sheets that cover continents. The most recent ice age, which peaked about 20,000 years ago, saw ice sheets more than 3 kilometers thick covering much of North America and Northern Europe. These ice sheets took tens of thousands of years to build up and began to retreat about 15,000 years ago. They are still retreating today in some places. The process of glaciation and deglaciation happens on timescales of tens of thousands of years, driven by orbital variations that themselves take tens of thousands of years to complete their cycles. Even within our own solar system, within the familiar space surrounding Earth, time moves with extraordinary patience. The Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. This happens because of tidal interactions between Earth and the Moon. The Moon's gravity raises tidal bulges on Earth, and Earth's rotation carries these bulges slightly ahead of the Moon's position. The gravitational pull of these bulges pulls the Moon forward in its orbit, causing it to gradually spiral outward. 3.8 centimeters per year is a tiny distance, but over millions of years it adds up. When the Moon first formed, about 4.5 billion years ago, it may have been as close as 22,000 kilometers from Earth, roughly 15 times closer than it is today. The current distance is about 384,000 kilometers. Over billions of years, the Moon has been slowly drifting away, and it will continue to do so for billions more until tidal locking between Earth and the Moon becomes complete and the drift stops. As the Moon drifts away, its orbital period increases and Earth's rotation slows. Currently, Earth rotates once every 24 hours, and the Moon orbits once every 27.3 days. But billions of years ago, when the Moon was closer, Earth rotated faster and the moon orbited more quickly. Days were shorter. A day on early Earth may have been only 5 or 6 hours long. The moon would have appeared much larger in the sky and would have orbited Earth in just a few days. This slowing of Earth's rotation and the lengthening of the day is ongoing. Earth's day is getting longer by about 1.7 milliseconds per century. This is an incredibly slow change. Over a human lifetime, the day lengthens by only about 1,000th of a second. But over hundreds of millions of years, the effect is significant. When dinosaurs walked the Earth, a day was about 23 hours long. When the first complex life emerged in the oceans, a day may have been only 21 or 22 hours long. These are the subtle, patient changes that accumulate over geological time. They are imperceptible on human timescales, but profound over the age of the planet. The moon drifts away, centimeter by centimeter. Earth's rotation slows, millisecond by millisecond per century. And the dance between Earth and moon slowly evolves, playing out over billions of years. Eventually, in the far future, Earth and the moon will become tidally locked to each other, meaning Earth will rotate exactly once per lunar orbit. At that point, one side of Earth will always face the moon, and one side of the moon will always face Earth, just as one side of the moon already always faces Earth today. This configuration is stable, and once reached, the moon will no longer drift away. But reaching this point will take tens of billions of years, longer than the sun has left to live. Before tidal locking is complete, the sun will have evolved into a red giant, expanding to perhaps 100 times its current radius. It will likely engulf Mercury and Venus and may reach out to Earth's orbit. If Earth survives this phase, it will be a scorched, lifeless rock, all its water and atmosphere long since boiled away. The moon may survive as well, still orbiting its dead parent world, but both will be little more than cinders in the outer envelope of a dying star. But even this dramatic fate is billions of years away. 5 billion years to be approximate. In the meantime, Earth and the moon will continue their patient dance, the moon drifting slowly outward, Earth's rotation gradually slowing, both locked in a gravitational embrace that has endured for 4.5 billion years and will endure for billions more. There is something almost poetic about these cosmic dances. The moon and Earth, bound together by gravity, slowly evolving over timescales that dwarf human comprehension. The sun and its planets orbiting the galactic center in a journey that takes hundreds of millions of years. The galaxy itself rotating slowly, its spiral arms gracefully turning over hundreds of millions of years while it drifts through space toward an eventual collision with Andromeda. All of these motions, all of these changes, happen with a slowness that seems almost deliberate, as if the universe itself is being careful, taking its time, ensuring that each step in, the cosmic dance is executed with precision and patience. And within this slow cosmic ballet, we exist. Brief sparks of consciousness, aware of our surroundings, capable of measuring these vast timescales and contemplating their meaning. We are the universe examining itself, brief moments of self-awareness arising in a cosmos that is mostly unaware, mostly composed of unconscious matter, following the deterministic laws of physics. Our brevity does not diminish our significance. If anything, it makes our existence more remarkable. That in a universe so vast and so patient, where change happens over millions and billions of years, there are brief moments where matter organizes itself into forms complex enough to think, to wonder, to understand. We are those moments. We are the universe, temporarily awakened, looking back at its own history and forward to its own future. Throughout this journey, we have encountered many different rhythms, many different timescales. Some processes happen in attoseconds. Others take googles of years. But all of them, from the fastest to the slowest, are part of the same universe, governed by the same physical laws, operating according to the same fundamental principles. There is a harmony to these different timescales, a way in which they fit together to create the universe as we observe it. The rapid quantum processes that happen in atoms are what make chemistry possible, and chemistry is what makes stars possible, and stars are what make galaxies possible, and galaxies are what make the large-scale structure of the universe possible. Each level builds on the levels below it. The slow processes emerge from the accumulation of fast processes. A star burns for billions of years, but each moment of that burning consists of quadrillions of individual fusion reactions, each happening in a fraction of a second. Continental drift happens at centimeters per year, but it is driven by convection currents in the mantle, which are themselves driven by the motion of individual atoms and molecules responding to heat and pressure. The universe is a hierarchy of timescales, from the Planck time to the evaporation of black holes, each level connected to the others, each process influencing and being influenced by processes on other timescales. And within this hierarchy, there is a kind of stability. The laws of physics do not change with time, as far as we can tell. The same equations that described the universe 13 billion years ago still describe it today, and will still describe it 13 billion years from now. The speed of light is constant. The gravitational constant is constant. The fundamental forces operate in the same way regardless of when or where in the universe you measure them. This constancy is what makes the slow cosmic processes predictable. We can calculate how long a red dwarf will burn because we know the rate of nuclear fusion and the amount of fuel available. We can predict the orbit of the Sun around the galaxy because we know the laws of gravitation and can measure the distribution of mass in the galaxy. We can estimate the evaporation time of black holes because we understand quantum field theory in curved space-time. The universe is knowable. It follows rules, and those rules play out over vast timescales with perfect consistency and infinite patience. There is comfort in this predictability. It means that despite all the uncertainty in our individual lives, despite all the randomness and chaos that we experience on human timescales, there is an underlying order to reality. The stars will continue to burn. The continents will continue to drift. The galaxy will continue to rotate. And all of these processes will unfold exactly as physics predicts they will, patient and inexorable. This is not to say that the universe is deterministic in every detail. Quantum mechanics introduces fundamental randomness at the smallest scales. We cannot predict exactly when a particular radioactive atom will decay, or exactly where an electron will be found when we measure its position. But we can predict the statistical behavior of large numbers of atoms, large numbers of electrons. And those statistical predictions are extraordinarily accurate. The slow cosmic processes we have explored are built on the statistical behavior of enormous numbers of particles. A star contains something like 10 to the 57 atoms. Even though the behavior of each individual atom is subject to quantum uncertainty, the collective behavior of 10 to the 57 atoms is highly predictable. The randomness averages out. The star burns at a rate determined by its mass and composition, following patterns that have been consistent for billions of years. In this way, order emerges from chaos. Predictability emerges from randomness. The slow, patient processes of the cosmos arise from the frenetic, unpredictable activity of individual particles, averaged over incomprehensible numbers and incomprehensible timescales. And we, as observers, get to witness this emergence. We get to see how the universe organizes itself, how simple rules applied consistently over vast spans of time give rise to the rich complexity we observe. Stars and planets and galaxies and life itself, all emerging from the patient application of physical law to matter and energy over billions of years. This emergence is ongoing. The universe is still organizing itself, still evolving, still creating new structures and new complexity. Stars are still forming in molecular clouds. Planets are still coalescing from protoplanetary disks. Galaxies are still colliding and merging. Life, at least on Earth and possibly elsewhere, is still evolving, still adapting, still becoming more complex. We are living in the middle of this process. The universe is not finished. It is still unfolding, still revealing new aspects of itself, still creating new possibilities. And this unfolding will continue for trillions of years, long after we are gone, following the same patient rhythms we have explored tonight. There is something deeply satisfying about understanding these rhythms. It connects us to something larger than ourselves, something that transcends our individual existence and our individual concerns. We are part of a process that began 13.8 billion years ago and will continue for timescales we can barely imagine. And in that continuity, that vast sweep of cosmic time, there is a kind of meaning, or at least a kind of context that makes our brief lives feel connected to something enduring. We have traveled together through deep time, from the birth of the universe to its distant future, from the quantum flicker of electron transitions to the patient evaporation of black holes. We have explored stellar lifespans measured in trillions of years, continental drift measured in centimeters per year, and galactic orbits measured in hundreds of millions of years. These are the slowest facts about the cosmos, the most patient processes, the rhythms that unfold over timescales so vast that they challenge comprehension. And yet, they are all part of the same universe that we inhabit, the same reality that surrounds us in this moment. The universe is not in a hurry. It moves at its own pace, following the laws of physics with perfect consistency, whether across attoseconds or googles of years. And in that patient unfolding, there is a lesson for us if we choose to hear it. That change does not need to be fast to be profound. That persistence and patience are fundamental features of reality. That the most enduring things are often the slowest ones. As you rest now, perhaps drifting towards sleep, you can know that you are held by processes far larger and longer-lived than yourself. The earth beneath you is drifting on its tectonic plates. The sun is orbiting the galaxy. Light from distant stars is arriving, having traveled for years or centuries to reach this moment. And far in the future, long after we are gone, stars will continue to burn, continents will continue to drift, and the universe will continue its patient journey toward equilibrium. There is nowhere you need to be, nothing you need to do. The cosmos will unfold at its own pace, with or without your attention. And in that knowledge, there can be rest. There can be stillness. There can be a quiet recognition that you are part of something vast and ancient and patient, something that will continue long after your brief moment has passed. The universe has been here for 13.8 billion years. It will be here for trillions more. And in this moment, you are suspended in that vast sweep of time, held by gravity and chemistry and the patient processes that govern all of existence. You are safe. You are part of this, and the universe, in its infinite patience, will carry on. Rest in that knowledge. Let it settle over you like a gentle blanket. The stars are still shining. The moon is still slowly drifting away. The continents are still moving beneath your feet. All of these processes continue, patient and unhurried, whether you are awake to witness them or sleeping peacefully. The cosmic rhythms do not require your attention. They do not demand anything of you. They simply are, existing as they have for billions of years, as they will for billions more. And you, for this brief moment, get to be part of them. You get to exist within this grand, slow unfolding, held safely in the embrace of physical law and cosmic time. So rest, drift, let go. The universe will still be here when you wake, continuing its patient dance through space and time, just as it has always done, just as it always will. Thank you for joining me on this journey through the slowest processes in the cosmos. I hope these facts have brought you some sense of peace, some recognition of the vast timescales on which the universe operates, and perhaps a little perspective on your own place in this grand, patient unfolding. If you found this exploration calming, if it helped you drift toward rest, or simply gave you a moment of quiet contemplation, I would be grateful if you would consider liking this video and subscribing to the Nebula Nights channel. There are many more cosmic journeys we can take together, many more slow facts and patient processes to explore, each one an opportunity to step back from the rush of daily life and remember the vast, unhurried rhythms of the universe. Until next time, rest well. The stars will still be there when you wake, continuing their slow dance through the cosmos, just as they have for billions of years, just as they will for trillions more.